All right. So now that we have all the questions of lecture 1 out of the way, thank you by the way for all your fantastic questions. Let's move on to chapter 2. And chapter 2 will be kind of, be a little bit more concrete. We'll see some kind of real code. First one was like a little bit dry. On the last slide we saw some code, but we cannot have a lecture on functional programming without code. If you want to play with Haskell, there's a couple of possibilities, as I mentioned in the first lecture. Graham kind of mentions here Hucks. Hucks you can kind of download. It's a very lightweight Haskell system, but you can also use GHCI, which is the kind of interactive REPL loop for GHC. Just search around on the web, or you go to haskell.org. And you can find your favorite Haskell implementation. They're all kind of very similar, the way they kind of interact with the user. I think GHCI actually is tried to be kind of Hucks compatible, so that should be no problem. And this is kind of one of the things that is quite amazing if you or amazing, not really. If you look at the ML, which was, as I said, designed as a scripting language for proofs, so most functional programming environments, whether it's Haskell or Scheme or F#, all have this notion of a REPL loop. And a REPL loop is not something that's kind of unique to dynamic languages like Python or Ruby or whatever. Actually, I would say a lot of the functional languages have REPL loops as part of their experience, and they have the kind of same console-based IDE, just like a lot of the scripting languages. So you type in Hucks, and then you get a prompt, and then you can type in expressions. So you can just type in expressions, and then you get the answer. So it's like very much like a calculator. The nice thing about Haskell is that since it's pure, this is a very natural thing, because every expression is not depending on state or previously executed expressions. So the notion of a REPL loop is very natural, because you just type in an expression that is a self-contained thing, and you execute it, and you get the answer. So what kind of comes with Haskell? So Haskell has like a Prelude. What like the BCL of Haskell is called the Prelude. It sounds like impressive, but really think of that as just the base class libraries, and it has kind of operations on lists like head. In Link we have head 2, I think it's called first. The names are slightly different. But if you're in C#, you have to write, a whole program. You have to kind of, write, using statements, and then you have to like a namespace and a class main. And, by the time you've written, console.writeLine, head of this, you have written like, I don't know, 50 lines of code. And then you have to kind of, hit F5 and it kind of runs. And I think the REPL loop gives you this kind of really kind of quick, lightweight experience, where you can just type in an expression, get the result, so you can experiment with your code. And again, if you use F#, it has a kind of beautiful REPL loop where you kind of scrape over an expression, and it kind of gets dumped in the REPL loop, and you can see the result. My dream is that one day C# will have a REPL loop. VB used to have a REPL loop in VB6, and hopefully that will come back as well. Because that kind of really interactive experience, I think, makes it really nice to just try things out, and then you write your real code. So it's a very different way to approach the problem. So let's look at a couple of more kind of Haskell expressions. So if I have a list, I can take the tail of the list, which kind of drops the first element. So if you type tail of that list, it will tell you immediately what is the result. Indexing in Haskell, is done by this double exclamation mark. So if I want to have the second element of the list, you know, I'll get number 3 here. I think, you know, it would have been slightly clearer if you started with 0, but, you know, lists are indexed, you know, with starting at 0, just like, you know, other things, most other programming languages. And then this one, you know, you will recognize that from LINQ as well. I can take the first 3 elements and then I just drop all the rest. So just playing around with expressions is really, really easy using this REPL loop. Let's look at some other expressions. Again, I really recommend to you to go to look at LINQ, system collections, whatever LINQ, look at all the standard sequence operators, and you will recognize most of the operators or the things that I show you here are in LINQ as well. And in fact, you know, when we designed the libraries for LINQ, you know, we looked at the Haskell Prelude to see, you know, which kind of operations on LINQ, on lists make sense. So all these things, you know, here that work on lists here work on IEnumerable, or, you know, on IEnumerable, and all other languages, or sorry, all other types that implement the sequence operators. So take and drop. That's the kind of, you know, these are each other's complement. So where take takes the first n elements, drop kind of forgets the first n elements, and then it just leaves the rest. So one of the things that you can prove is that if you have a list x's and I say, you know, take you know, n x's, and I append drop, and I think this is n minus 1, and I have to drop x's, then I get the same, no, it's even n. So you always have to kind of be careful where you count. So if I take the first n and I drop everything but the first n, I get back the list. So these are things that kind of, you know, Haskell people like to prove, where, you know, that's like, in some sense, this is the way you define how take and drop should behave. Okay, so you're often writing code where you have to break up a list. You know, again, like remember the quicksort example. If you're writing an algorithm on a list, you want to kind of break the list into sublists and then work recursively on each of the sublists. So this kind of, you know, take and drop is kind of, you know, a nice way to take a list and kind of, you know, break it up in 2 parts. And now I know by this definition that this is actually breaking up that list. And this kind of, you know, that kind of equational reasoning is something that you can do in a purely functional language. Let's look at a couple of other functions. Length just takes the length of the list. Sum, we have seen that last time, you know, that just kind of sums all the elements. And again, you see here, you know, the very powerful way of writing expressions. And something that's kind of weird, that might look weird, is that, you know, I write drop space, 3 space, and a list. Whereas in an imperative language, you would probably write, you know, 1, 2, 3, dot, drop of 3, instead of drop 3. Okay, so this is like, you know, C#. This is Haskell. And then in F#, you would write something like 1, 2, 3, I think. And now, you know, of course, I don't have an F# implementation, you know, drop 3. Something like that, where, you know, and where this operator is really defined as, you know, I can write that down. It's like, you know, x's f is defined as f x's. So you can kind of define syntactic sugar, just define a little function that allows you to kind of, instead of writing it in kind of this weird way, you can write it in a kind of, you know, more, you know, object-oriented way where you're kind of, applying the method f to the object axis, which is really what I'm saying. I'm applying the function f to the object axis. So there's, kind of, the different ways that people write code, but it does show the kind of difference between object-oriented programming and functional programming. Object-oriented programming, usually this guy, and let me wipe out this guy. If you look at objects, you really write, a receiver dot method, and then you write the arguments, A, B, C. So in object-oriented programming, the receiver, the instance of the object is the most important thing. And one way to look at it is I'm sending this message to that object. In functional programming, the arguments usually, there's no single argument that's more important. Okay, and again, if you look at objects, this guy, if this is a virtual method, it kind of does dynamic, based on the dynamic type of this, it will do a dynamic dispatch. So it's kind of the receiver that's the most important thing. In functional programming, you just write method, receiver, A, B, C in Haskell. So this is again C#, Haskell. And really, none of the arguments is more important than the other. And if you look at pattern matching, the method can be defined by pattern matching, by matching on each of these arguments. So in some sense, that's what people call an object-oriented program multi-methods. So I can kind of dispatch on the dynamic, this method can dispatch, pattern match, on the dynamic values or the dynamic types of any of its arguments. So that's kind of a big difference. Whereas in objects, there's this single thing that's the most important thing that receives the method and thus the dynamic dispatch. Whereas here you can do dispatch over all these things. And if you want to do multiple dispatch, you usually get this kind of weird thing that you use in the visitor pattern where you're doing a double dispatch. So in here you then kind of dispatch over these arguments. Pattern matching is, I think, an easier way to do exactly the same. But I consider pattern matching and dynamic dispatch to be equivalent. They're trying to do the same thing. Based on the dynamic type of the arguments, you're trying to kind of, call a different version of the method. So that's a little excursion into, the kind of philosophy of how you view functions and objects. So another way to look at it is that in functional programming, this guy is the most important thing. In object-oriented programming, that guy is the most important thing. So that's why it's called object-oriented programming, because the object is the most important thing. And here it's called functional programming because it's the function that's the most important thing. And it takes the objects as arguments, whereas here the objects takes the method, the message as an argument. That is, the way I kind of, compare and contrast these two worlds. So I've shown you here, a lot of examples that all were little expressions on lists. That's another kind of interesting thing, is that in Haskell or in many functional languages, if you look at Clojure or Scheme or Lisp, lists are the kind of, the data structure. So in Haskell you often find yourself, and in Lisp it's even more true, you never define really a data structure because you do everything with lists. So list is kind of the universal building block. So everything you write is done using lists, which is very interesting because now you see that the language contains a lot of syntactic sugar for lists. So because lists are so fundamental, the language is all geared towards having lists. And we will see really that this is syntactic sugar for a set of constructor calls to create a list. So lists are very, very important in these functional languages, in most functional languages. All right, so let's talk a little bit more again about syntax. So the idea of Haskell is kind of inspired by mathematics, but it's slightly different. So let's look at this expression here. So if you write math, you write I'm applying this function f to a and b, and I add c space d. And if in your typical math textbook or physics textbooks, or Brian Beckman would say, yes, of course, this is multiplication, right? Because if you're doing physics, the operator that you use most, you make it the smallest. That's kind of one of the rules of language design. The operator you use most takes the least amount of space. So in some sense, in objects, when you write x's dot method, right, this is the operator you use most, so you give it the least space. And maybe you can even argue, and probably Gila Braga would argue, that this is blood, and because you're doing method calls all the time, you should not even use a dot, you should use a space for that, or something like that. And then you go, Smalltalk, I think, has kind of similar syntax where you have, you can write these things without any of the dots. On the other hand, I really like the dot in object-oriented programming because, in the IDE I can type the dot and now I get IntelliSense, that tells me all the things that I can do on that object, which is a very nice kind of side effect of the object-oriented way of thinking, that because this thing is the important thing, I can type dot and it will tell me in the IDE what I can do to that object. And I don't know whether that was by design or by accident, but that is, the fact that the IDE can help you in an object-oriented language, I think is a super important thing, which is much more difficult in functional programming because, if I'm waiting here in my IDE, what do I type? Right? I don't have anything to type because I don't know which functions I can call at this point. So I think, the way you kind of program in C# or in VB or Java is kind of much more fluent because you can kind of have the IDE drive you forward, whereas in functional programming you have to take the initiative, whereas in object-oriented programming the IDE can kind of help you along, which is actually one of the reasons for practical programming I prefer to use C# because I don't have to learn all the libraries, I don't have to remember the millions of methods. I just have an object and I type dot and the IDE tells me what I can do with it. But again, little excursion is you want to make the operator you use most to give that the least weight. So it must be the light, it must be space or dot or something small. And usually in physics that's multiplication, but in Haskell it's application. So application is used with space. So in Haskell you would write this as f applied to a applied to b plus c times d. And here you see that application is a space. And then we'll talk a little bit about this weird thing here as well. So why do we write f a b and not f a comma b? And what we will see is that these are two very different ways, very different functions. They are very different, and we'll come back to that. Okay. The other thing is that not only do you want to give the operator that you use most, the kind of least weight syntactically, you want to have semantically bind it as strong as possible. So if you write fa plus b, that space, that application binds strongest. So now you can write, instead of putting parentheses, you can now just write fa plus b. This might all sound like a little bit kind of, like I'm doing like, some like poems or like twiddling around. But in Haskell it's very important. So the Haskell syntax is really optimized to make it kind of, look nice and lightweight. So there's no noise. It's very, very noiseless. Whereas if you look at objects, again, there's a lot of noise. There's dots and parentheses and whatever. And Haskell is very much optimized to have a lot of white space. So it's very light, very fluffy syntax. And as we will see also, like there's offset rules, so you don't have to write curly brace open, curly brace close. And that's one of the things that I like very much about Haskell is the syntax. It just, and of course, it's really the semantics that's important, but I mean, there's very, very few languages that look as beautiful and elegant where your programs look so nice as in Haskell. And that's, so often, people tend to kind of polish their Haskell code even more because, when you write something, it's like, I can write it even nicer, that it looks nicer, and you get these very, very beautiful programs that are then probably very hard to read because, they get more and more compressed and more polished. So there's a downside to that too. Anyway, let's look at, a couple of examples again. So in mathematics, you usually write f of x if you know from high school math, right? In Haskell, you don't write the parentheses. Here, if I have two arguments, you just write them like that. And here you can already see, lots and lots of parentheses, lots of noise. And in Haskell, you only write parentheses where you really need it, where, in this case, I want to apply f to x and g of y. Well, I apply f to x, and if I would leave out these parentheses, I would pass g and y to f, so I have to put parentheses here. But you like in most cases, you don't have to write any parentheses. And if you look in the book and in normal Haskell programs, there's even tricks that people use to write even less parentheses, where they have like the dollar operator, which is like a right associative application. I don't know, this would be a good question to the viewers. Would you appreciate if we would talk more about all the tricks that Haskell people use to write their code in a more compact way. So there's a whole kind of subculture of being able to write very concise code where you can, I can replace these two parentheses by writing a dollar instead of, the space here. So I've saved one character. And the Haskell people are geeks where they kind of, that's an improvement. So I have one character less. And so there's lots and lots of tricks that people use to write shorter code and get rid of single characters. So if you're interested in, drilling down into that, leave a question on the website and I'm happy to dive into that. All right. So, of course, in Haskell you can not only use the standard Prelude, but you can also use your own functions, and you do that in a script file that typically has a .hs extension, just like a C# file has a .cs extension. So that's, you can recognize, Haskell programmers when they have lots of .hs files on their system. Okay, so here's how you define a new function. So in Haskell, again, it's very lightweight. If I want to define a new function that kind of, doubles its argument, I just write double x equals x plus x. And if I want to write a function that kind of, quadruples its argument, I just call double twice. And this is, let me give you an example here, right here, of how, a real Haskell programmer, would write this. Because here, you look at this example here, and it's like, there's lots of redundancy here. If I look at this, I say, there's parentheses here, there's this x here, too much noise. So a real Haskell programmer would write quadruple equals double compose double. Where, f compose g of x equals f of g of x. So this is the definition of composition. So now you can see that I've kind of written that function here that took, I've now lost 1, 2, 3, 4. I dropped 4 characters for 1 extra one. So now, you know, Haskell programmers are really happy. He will go to his wife and says, you know, darling, you know, I've written this beautiful piece of code. But again, that's the kind of, you know, attention to detail that, you know, that Haskell programmers do. And again, this is not something that you can write in C#. So in C#, you know, you cannot write a function without, you know, having arguments. But here I'm just writing an expression which is a composition of 2 functions, and there's no reason I have to pass any arguments because, you know, it will it's just the composition of 2 functions. Another thing, and if you're an F# programmer, you will recognize that I didn't have to write any types, right? I didn't write any types here, but it's not dynamically typed. The compiler infers the type for this guy, and in this case, double or quadruple will have type, the following type. So it says it's a function from A to A, but it's not for all A, it's only for A that are numbers. And why does it know that it's only for A's that are numbers? It's because I use addition. Okay, so this is like an interface. So this is like in C# when you have generic types, where you have constraints. So let's say, what would be the C#? Let me try to kind of, you know, the C# type. Quadruple of T returns a T and takes a Tx, and then it does return double of x, and then here I have to write where T inherits from, you know, I numeric, or I num, let me just write I num of T, something like this. So this is approximately what you write in C#. This would be like I equatable or something, so it means that, you know, I can do numeric operations on T, so it's not for all T, so it's constrained, but here you can see, you know, I don't have to write this. So this is the Haskell one, and this is the shortest program, kind of equivalent program that I write in C#. So you can see, you know, how much more noise there is here compared to here. Because really, if you look at this code, the only 3 things that are important, and I should, next time we should have more colors. The only important information in this code is the name of the function and the fact that it calls double twice. Okay, and all the rest is noise, or what Gilad Braga calls blood. So he would write all that other stuff in red, and you see here in Haskell, you know, you only write the essence. That's the importance of that function, and all the rest, this ceremony, you don't have to write. So that's, but again, you know, this one might be easier to read because here you have to kind of uncompress a lot of that stuff that's implicit in that code. All right. And now, once you load that file that contains that definition, now you can just again use the REPL loop. Ah, fantastic. More colors. So now you can use that the functions that you just defined and just can you can call them. So if I quadruple 10, well, I expect to get 40, and now I can kind of take double of 2, which is 4. And now, so I can take the first 4 elements of this list. And here again, you see this kind of very expression-oriented style where I write this kind of complicated expression here that, uses all kind of, functions to do something more complicated. But what I want to stress here is that because all these functions are, functions here, like in C#, let's write, I'll use blue. No, I use green, but I mean red. So in C#, in a method, if this was in a class, oh, I forgot even that, right? I have to define this in a class X, so there was even more noise. But inside that class, I can have here, you know, some state. So I can have here, you know, TS. And then in here, I can now say, you know, S plus equals X. Right? I can, inside that method, I can just side effect the state of my object. Now, that's the kind of big difference. In Haskell, I can always call this function in isolation. It never depends on the state. Whereas in C#, you know, I cannot call quadruple just by itself. I always must pass it its instance because that's where it kind of, you know, mutates its state. So it's much harder to test this quadruple thing in isolation because I always have to, you know, use it in its context. And that's what you see a lot with the test framework, like unit tests, where, you know, you first set up stuff, you run your test, and then you tear down everything. That's kind of, you know, indication that, you know, in order to run a method, it has to live in some context, in some stateful context, whereas, you know, testing these guys, it's much easier. And again, you know, if you want to, there's like a lot of interesting stuff on testing functional programs, like Quick Check or something where you kind of generate test cases automatically, which is all much easier because, you know, all these functions can live in isolation. You can take them apart and just test them here. They don't have to live in this global state. All right. So now let's look at some more kind of Haskell code. So if you want to define like a factorial, so you would think, oh, factorial, again, you know, not that is a very useful function, but if you would do that in C#, you would probably either use a for loop or you use recursion. Well, in Haskell, you know, we hardly ever use recursion, but we kind of, you know, again, we build these things out of building blocks. So first you say, what is factorial? Well, it's, you know, really, it's like 1 times 2 times 3 times n. So this is the kind of thing that I want to do. So how do I get there? Well, if I just first create a list of the numbers 1 to n, and then I just multiply them. So that's exactly what you write here. So the way you think about this is in a very compositional way. It's like you break it up in 2 parts. Well, I first need to generate a list of numbers, and then I take the product. And that way of compositional thinking, you can only do that because it's a lazy language. So let me kind of write another example. And you have this kind of laziness with link, but in Haskell, you know, this allows you really to write things in a compositional style. So if I want to, you know, this guy creates the list, you know, 1 to up to n. Okay? So now imagine that we didn't have that, but I only had a way to create infinite lists. So I could write this, and that would be the infinite list 1, 2, 3, etc. Okay? So if that would be my primitive. Now I can define that guy by just saying, you know, take n of 1 dot dot. So this is like, you know, let's write that, call this guy x's. So I can say take the first n element of the infinite list. Since Haskell is lazy, this is okay, right? In C# or, you know, well, with enumerable that will work because it's lazy. But imagine that, you know, this is not a lazy language and I'm creating this list. Now, in order to call this take, it would just go off and, you know, evaluate that list and would never come back because it's an infinite list. In Haskell, I can just write this because this guy will be evaluated just enough to take the first n elements. So lazy evaluation is essential in writing compositional expressions because you know whenever you write an expression, each argument will only be evaluated just enough to compute the result. Whereas if you write in a strict language, you know, all the arguments will be evaluated all the way down. and so you might do more work, and now you're going to tweak your algorithm to kind of, you know, compensate for that eager evaluation. And that is something, you know, even a lot of Haskell people don't appreciate, is the fact that laziness gives you this compositionality. Of course, there's a price that you pay for it, because if you know that you need to use that whole argument, it's cheaper to kind of, you know, evaluate it in advance instead of keeping closures around. For example, if I now do, you know, product of take and one dot dot, the way this works is when I call product, it's not going to kind of evaluate that eagerly, it's kind of going to do that kind of on demand. And in this case, it might be more efficient to just kind of, you know, take this, create that list, and then just run the product. But so that's the price you pay, but what you get is compositionality, because now I can really build this thing out of, you know, subcomponents without having to worry about side effects and, you know, execution and non-termination. Everything gets evaluated just enough to produce the final result. Okay, so that was a kind of little excursion on lazy evaluation. We'll talk much more about lazy evaluation in future lectures. Then another thing, let's talk about back to syntax. We talked enough about semantics. In syntax in Haskell, you can write, you know, here's like this weird thing where I write div with these backticks. That allows you in Haskell to write a function as an infix operator. So if you write x backtick fy, that's just syntactic sugar for fxy. So you can write like, you can define your new infix operators just by kind of putting them inside these ticks. And again, you know, that's something you don't see in other languages, but now, you know, you can write this in a more like better reading way. So it's like, take the sum of, you know, these numbers and divide it by the length of that list. Instead of writing, you know, otherwise you would write div of some numbers and length numbers. So now compare this with that, and I think this looks nicer. Again, it's beauty of your code is very important for like pure functional programmers, and this looks very much Lispy, right? You know, let's even write some more parentheses about it, and now you have closure or scheme or whatever, and there's you know, let's like even put some more parentheses, you know. So this is what you would write in other languages, or in C#. You would write, you know, well, there's div, but, you know, in general, this is what you would write in a normal language. And look at all the parentheses, all that noise, and look how beautiful and clean it looks here. Okay, this is another interesting thing. Python has the same thing. In Haskell, you know, you have big nums. So if you can take the factorial of, you know, 100, and it will just print, you know, I think in C# probably if you use int32 factorial 14 or 15, then you already get overflow. Again, if you want to use numbers, you know, integers, or, you know, well, why don't you use big numbers? And again, of course, in C# or most languages, you don't do that for efficiency reasons, because you want to use the kind of machine words. But in Haskell, you know, that's another thing. It's like the correctness of your program is more important than the efficiency. And if you want to use int32 or int64, you can do that by kind of saying that's the type I want. But, you know, and numbers, it's like very much like in Python, you know, they're like big nums are kind of just part of the normal language. So it's like you don't have to do anything special. Okay, so this is, if you want to read Haskell code, there's a couple of conventions that people use, and syntactically, you know, this is a requirement. So in Haskell, functions and arguments must start with lowercase. So the reason is that in Haskell, you don't, when I define this thing here, I define x is equals, remember that I didn't say, you know, function, you know, or let me, because this is not even a function. let's write the factorial example again. If I write factorial of n was product of 1 to n. Remember that I didn't tell you that this was a function definition, so I didn't write function or anything or definition. So the kind of namespace of functions and types is kind of distinguished by the fact whether, you know, this thing starts with a lowercase or uppercase. So type names always start with an uppercase. So in Haskell, if I define a list, you write, you know, data list of A equals, you know, whatever. So type names start with uppercase, and variable names and function names start with lowercase. So that's kind of, you know, I have not seen that in many languages where, you know, you're using the fact, you know, whether the case of the first letter to kind of, you know, distinguish what kind of value this is. But again, now the compiler knows whenever it sees this thing, you know, that this is a variable and not a type. So it's kind of, there's some saneness in that. But it means that, I don't know, I always forget, it's like camel case or, you know, Pascal casing, but you're forced to use one or the other for your functions and classes. And in some sense, maybe C# does that by convention anyway, and here it's just enforced. Then the other thing is that Haskell people kind of use a little bit of Hungarian notation. Again, because there's no required types, you still want to kind of, you know by looking at your function definition what the types are. So usually when there's a number, you call it n, but when you call it, when it's a list, you usually call it something that ends with s. So this is like x's. So this is like 0 or more x's. And if you have a list of lists, you know, like flatten, if you define flatten, then you write 2 s's. So now you say this is a list of lists. So, and this would be a list of numbers. So people use this kind of Hungarian notation that from the kind of name of the arguments or something, you can kind of get a little bit of a hint what the kind of structure is of the type. So you don't have to really look at the type. And again, in C# and VB we do the same, or in .NET framework, right? Interfaces start with I. So there's a little bit of that convention, not as much as in the olden days, you know, in C++, but, you know, a little bit of, you know, it's like a little bit of salt on your program is makes it more tasty. Okay, then this is like a controversial issue. People love it or hate it. I tend to love it. This is significant white space in your code. So in Haskell, you know, when you have a sequence of definitions, they all must start in the same column. So if you know here, you know, this one starts a little bit further away, and this one starts like one space further, that's not allowed, because layout is used to indicate block structure. And Python uses the same convention. Haskell's layout rule is very sophisticated and more complex than Python. But like ISWIM, the language that we talked about, Peter Landen's language that we talked about in the first lecture, introduced that idea of significant white space. And again, the whole reason is that, you know, instead of writing begin, end, or curly opens for block structure, you just want to have the layout, you know, if you look at it, you immediately see. I mean, let's write, you know, some C#. If I write if E curly open, and then people usually, you know, they statement, 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 curly close, else, oh, else, statement, statement, statement. So people kind of, it's redundant if you look at it, right? Because you're using indentation and I'm using curlies to indicate block structure. And so in Haskell what people say is, look, because you indent here, I don't have to write these crazy curly braces, because the compiler can infer it, because it knows that, you know, you're indenting here, the fact that, you know, there's indentation here means that the block starts. The fact that, you know, you're indented kind of here at the same level means that your block has ended. So it's really using the layout of your code to convey the meaning of the code instead of having to put all these brackets. And again, it all has to do with this weird, perverse desire to write beautiful code. Okay, it's super important for Haskell people to write beautiful code. Interestingly, when I first started to kind of, you know, program in F#, you know, I really missed this. I really missed the kind of layout rule. So I kind of complained to Don Simon. I said, you know, I missed the kind of layout rule. And then Don implemented the kind of lightweight syntax in F#, which allows you to do the same thing. So thanks, Don. That was like, you know, super, super cool of you. And I think now the lightweight syntax is even the default in F#. So again, you see there, you know, it's like writing beautiful code. I think also often means correct code, you know, because you give love to your code. And if your code looks good and you're paying attention to it, it's like grooming your dog or your cat. Right? Giving it love improves the quality. And Haskell and the ability to write beautiful code, you know, just enhances the fact that you can give love to your code. So I think that's goodness. Okay? So here's the layout rule. So in Haskell I can write this thing here, and what it really means is this thing with, like, you know, curly brackets and semicolons. So in Haskell you can write curly braces and semicolons if you want to, but you don't have to. And often this is easier if you generate code mechanically, because then you don't have to calculate this layout. But for a human, I mean, everybody has to kind of admit that this looks much more beautiful than here, because there's all that noise, right? If you really want to kind of, you know, write code, you only want to convey the essence. And all this other stuff is just a distraction. It doesn't really, you know, this is something that I have to write down to help the parser, okay? That's not something that helps me solve my problem, that curly brace and semicolon. So in Haskell, you only write down what is essential to solve your problem. But the compiler goes out of the way to kind of, you know, infer all the rest. So it infers the block structure, it infers the types, everything. So you only specify the essence. And that's important. It's like, you know, it's boiling down all the noise, removing all the noise, so you write, you know, something beautiful that expresses only what you want to express, instead of kind of having all that, you know. This is like a car, an old-fashioned car with a crank where you have to start it, you know. And here it's like the car where you just walk to it and it knows, you know, because you have an RFID and it starts for you automatically. That is the difference. Sophisticated, old-fashioned. Okay, well, this is, if you want to use Hucks, you know, you can do certain commands. I'll skip that, you know, that's something if you play with Hucks or GHCI, you know, you just type : and you get all the commands. All right, so this is the end of the second lecture, and again we end with some homework, and the homework is really easy. There's no, you know, just play with Haskell. Install GHCI, install Hucks, and just play around, you know, try some of the examples, try to, you know, write some code like this, where, you know, your offside rule, you know, here you see that this X starts like in one space to the left, so that's, you know, you will get a syntax error. Play with that, you know, get a feeling of, you know, how you write code in this way, you know, like try to kind of, you know, write this instead of with these backticks, write it with parentheses and prefix notation. Then there's some more interesting exercises here. For example, I've shown you how I could define, you know, this function that generates a list from 1 to n. Like there, we also saw this thing that takes the last element of a list. Now try to define last using, you know, the functions that were introduced here. So how can I define last? Does it have to be built in? Think about it. If I have a list, how can I get at the last element? Just, you know, how would you explain this to a 4-year-old, you know, to select the last list? And that's what you write down, and that's your Haskell solution. Okay, and then, you know, of course you can do another definition if you're, and probably here you say, oh, I can use recursion, I can kind of do explicit recursion. This one, but that's not what you would explain to your 4-year-old, right? There's a very easy way, so you can define that. And the same here is another function init, and again, the way to find out what init does is to go on the web or look in the Prelude. There's a very good overview of the Haskell Prelude that kind of, you know, gives you, I think Arjan van IJzendoorn wrote that with some other people, that kind of explain for all the functions in the Prelude what they do with small examples, and then just try to kind of define one yourself. And again, try to do that in a compositional way by gluing together simpler functions. So that was it for today. Again, thank you very much. You know, you have some homework, and of course send in your questions, and then next time when we do lecture 3 we will answer all your questions. And again, thank you for your attention, and I hope you kind of, you know, enjoy functional programming part 2.